All right, and welcome back. This is 9.8 part 2, and here's what I want to do in this video. I want to, first of all, I want to do an example and just kind of show you how we'll go about finding the center, radius of convergence, and interval of convergence for a kind of a general power series. And then I want to talk about this idea that I said earlier. We can think of a power series as an infinitely termed polynomial. And in fact, we can actually think of it as a function, and it's a function whose domain is its interval of convergence, which makes sense. That would be the ones where we would actually get an answer. Okay, but think about it. For a value of x, we get it converges to some value. So yeah, it makes sense to think of it as a function, and if we think of it as a function, then that leads to some other considerations, and we'll get there. All right, so to begin with, let's talk about this power series here. It's the sum from 0 to infinity of x minus 4 to the n over 2 to the n times n. Now, you might be looking at that and saying, there's something wrong with that. And in fact, there is. In this case, we really need to change this to from 1 to infinity. Because 0 right there, yeah, that would have caused a problem, having 0 on the bottom. So to avoid that, we're going to look at this series from 1 to infinity, which is a little different than our normal power series, but it's okay. We can deal with it. Everything works the same way. So from the very beginning, we can say that the center is going to be at 4. And the reason we can say that, remember, is because we have x minus 4, and x minus c is what determines our center, and c in this case would be 4. So there we go, it's the center. So we're a third of the way to our answers already. So now, remember, from that point, we move to the ratio test. And in particular, I'm wanting to know about the limit as n heads to infinity of the n plus 1th term. So I have x minus 4 to the n plus 1 over 2 n plus 1 times n plus 1. All of that over x minus 4 to the n over 2 to the n times n. All right, and all of that in absolute values. Now, in what you should be used to now, I'm fixing to do some rewriting here. I'm going to take the limit as n heads to infinity of, all right, and I'm going to split off this first x minus 4, and I'm going to write this as x minus 4 times x minus 4 to the n, that's this to the n plus 1 term, over 2 times 2 to the n, okay, I'm breaking this 2 to the n plus 1 up, and then n plus 1 I have to leave alone. Dividing by a fraction, we multiply by the reciprocal. So this is 2 to the n times n over x minus 4 to the n. Now, I didn't have to do all that splitting apart with algebra, but I like to do it because it makes it a little cleaner when I do this. When things start crossing out, then things just cross out wholesale. All right? And what am I left with? Well, I'm left with the limit as n heads to infinity of absolute value x minus 4 times n over 2 times n plus 1. All right, so that cleaned up a lot. Since this x minus 4 has absolutely no n in it, I can take it outside of the limit. It's still inside of absolute values, though. All right, so I have x minus 4 in absolute values times the limit as n heads to infinity of, and I don't even need absolutes anymore because our n starts at 1. Therefore, n and n plus 1 will both be positive. So this will be n over 2 times n plus 1. And I could do all the math, but I'm not going to. this limit's going to end up being 1/2. If you multiply this out, you'll have n over 2n plus 2. Then you have the same degree on top and bottom. The limit's going to be the ratio of the leading coefficients, which is 1/2. So this limit of all of this is going to be 1/2 times the absolute value of x minus 4. All right, now that's a lot of work. And I'm just going to go kind of a little out of the way we would normally do this. And I'm going to do the next part here because I don't want to erase that just yet. So now I'm going to come over here. The reason we do all that is because the ratio tells us that we have convergence whenever this limit is less than 1. So what I want to do is now I want to take that limit, 1/2 absolute x minus 4, and I want that to be less than 1. Well, when will that be happen? Multiply both sides by 2. That's whenever x minus 4 is less than 2. All right, now, whenever you get to this point and you have the absolute value of your variable or the expression containing your variable, like here I have x minus 4, less than 2, this is going to be my radius of convergence right there. So I'm going to go ahead and write that in. Now, if you didn't realize that, that's okay. We're going to get to where you can check it in just a minute. So let's look at how do we deal with these kind of inequalities. What this means is the absolute value is less than 2. That means that x minus 4 is between -2 and 2. Okay, that's what that absolute value means. If I want to solve this, then I have to add 4 to everything. This is a compound inequality. So I get 2 is less than x is less than 6. All right, what does this mean? This means I have convergence on the interval from 2 to 6 open, because that's where this limit is less than 1. Whenever x is between 2 and 6, this limit is less than 1, so we have convergence by the ratio test, which I didn't write up there. All right, but notice also our center is 4, and if you think about 4 being in the middle, what's the distance? From 4 to 2, the radius is 2. From 4 to 6, that distance is 2. So you can find the radius pretty simply. You know, if you don't realize that this is the radius here, then when you find your interval, we'll just, okay, what's the difference from distance from my center to the endpoints should be the same. And in this case, the distance from 4 to 2 is 2. The distance from 4 to 6 is also 2. The radius is 2. All right, now that part is pretty much consistent anytime we're asked to find the center and the radius of convergence. Now, if we're asked to actually find the interval of convergence, which in this case we are, then we have to consider what happens at the end points. So we need to know what happens at 2 and what happens at 6. All right? And we did this once before, but we did this in one that worked out very, well, there wasn't a whole lot of work to be done. So now let's check the endpoints. And I erased what I have, but I remember them. Let's what happens when x equals 2. Okay, when x equals 2, we're going to plug 2 in for x right there in our series. We get the series, which is the sum from 1 to infinity of 2 minus 4 to the n over 2 to the n times n. All right, so this is a particular series that I want to know if it converges or diverges. Okay, well that's going to be the sum from n equals 1 to infinity of -2 to the n over 2 to the n times n. Now there are a couple of ways you can do this. The way I like to do it is to kind of break it up like this. This is -1 to the n times 2 to the n over 2 to the n times n. and then these things just go away because they're the same. And what do we get? We get the sum from n equals 1 to infinity of negative 1 to the n, 1 over n. I can take that negative 1 to the n out front. What is this? This is the alternating harmonic series, which converges. So that means that we converge at 2. All right? So our interval of convergence is going to be closed at 2, and then it's going to go to 6. I don't know what happens at the end at 6 yet. I have to check that. But that. Now, what I could have done here is I could have said negative 2 to the n divided by 2 to the n is negative 1 to the n. You can do that because the powers are the same. I did not do that because sometimes that's not the clearest thing to do. And just because I like breaking things apart. There's something about that that I like. All right, so now, I'm going to cheat a little bit. I'm not going to rewrite everything. All right, what happens when x is 6? Then we get 6 minus 4. Well, what do we get? Well, 6 minus 4 is 2, so I get 2 to the n over 2 to the n. That means we have 2 to the n over 2 to the n times n. We can cross those out. And what are we left with? We're just left with 1 over n. What's the sum from n equal 1 to infinity of 1 over n? That's the harmonic series. That diverges. Remember, those two series, we know we know how they act. And so it's open at 6 because it diverged. And many, many, many times in these problems, especially the ones you're going to do, you will do this and you will find that one of the endpoints ends up being alternating harmonic series, the other ends up being the harmonic series. That happens a lot. It doesn't always happen, but it happens a lot. All right, now it's possible to get convergence on both sides. In fact, that happens a good bit. It's possible to have divergence on both endpoints. We've already had that. So, we've got to check it. There's no pattern. We have to check it in every case that we really want to know the full interval of convergence. All right, so I'm going to leave this here for just a second. I'm going to stop the video, and then I'm going to set up for the next thing. Okay, so now, here's what I want you to think about. I want you to think about the idea of a power series as a function. If we can think of a power series as a function, can we do things with that function that we can do with other functions, like take a derivative or an integral? And the answer is yes. And how does that work? And it's going to work exactly like you would think it was if you really thought through it. So let's look at this. Let's say we have a power series. And in fact, this power series convergence and r is greater than 0. So it's not that case where it just converges at the center. Because as I said, that's a bunch of zeros and it's boring. All right, so now let's define a function by the f of x is the sum of the power series. And look at this. This is what the power series looks like. A sub 0 plus a1 x minus c plus a2 x minus c squared plus, that is the generalized form of a polynomial, if you've ever seen that. It's just an infinite number of terms. All right? If this is a power series, the function defined by this power series, then it's differentiable on its interval of convergence. And in particular, it'll be on the open interval. So we're not really worried about the endpoints here. But it's differentiable on this open interval, which means it's continuous on that open interval. And that's important because now, if we take the derivative of this function, because it is continuous, we can, instead of taking the derivative of the sum, we can look at the sum of the derivatives. And what is the derivative of this? It's just a power rule. we're going to take the power down front. It's going to be n times a n x minus c to the n minus 1. That's exactly what it is. It's the power rule. Take your power down, multiply it out front, and then decrease your power by 1. The only difference is because we're taking a derivative, this first term here, a sub 0, is going to go away. So we change our index here. Okay? It's 1, just to kind of take account for that. This is beautiful. This allows us to generate different power series without having to go through the whole business again. All right, what about integrals? Same deal. The integral of f of x, which is, again, this power series, that's the integral of the sum, which we can think of as the sum of the integrals. And what is the integral of a power series? Well, we're going to add 1 to this power, n plus 1, and then divide everything by the new power. And we're going to add in a constant because this is an indefinite integral. So we have a constant, plus the sum of a n times, look, new power plus 1 over n plus 1. It's exactly what you would expect it to be using the power rule for derivatives and integrals. Okay? It's polynomials. It's just an infinite number of them. And we can do this. It's really cool. But what's even cooler than all that is if the radius of convergence for this original power series is r, the radius of convergence for the derivative and for the integral will also be r. So we don't have to go through all that business with the ratio test. We can know exactly what the radius of convergence is, but we do have to look at the endpoints to a point. And I'm going to say this, and I'm hoping I say this in a way that makes sense. I want you to think of integrals as going up, derivatives as going down, all right? If we are going from top to bottom and we lose an endpoint, like let's say when we take the derivative, all of a sudden that endpoint is not in the interval of convergence anymore, it never comes back. It's gone forever. All right? If we're going up and we gain an endpoint, like say we take an integral and all of a sudden we converge on the right where we didn't before, it's going to converge all the way up. It's easy to understand when you understand it. It's hard for me to put it in words. So now, all that remains is to do a problem with this stuff. So while I'm erasing, let me tell you why this is important. Remember what we're talking about. Where we're headed is we're trying to represent hard to calculate functions with a series, and in particular with a power series. Why? Because we're adding and subtracting. Well, why are we going to something that's infinite? Because in general, we can take we don't have to use the whole series. We can use just a finite number of terms and get whatever level of accuracy we really want. And then we can approximate our value as closely as we need to the actual value. And we can do that in a way that we can do by hand. And we'll talk more about that later. Representation of functions is really cool. And this is what we actually use in a lot of our computational systems. Computer-based stuff. So let's look at an example. Let's look at, let's see, we've got the sum from n equals 0 to infinity of x over 3 to the n. All right? So I want to find the center, the radius of convergence, and the integral of convergence. And we're going to define this as a function for f. Then we want to find it for f prime of x and the integral f of x dx. So to find all three of those is going to require us to find f prime and the integral of f and x. So let me just kind of lay out how this is going to work. We're going to find the center radius of convergence, interval of convergence for this series. Okay? That's going to require us to do the stuff with a ratio test. We're going to have to check the endpoints and get everything for this function. Once we do that, we're going to find f prime. Once we find f prime, we already know what the radius of convergence is. It's the same as this one. Okay? Then we just need to check the endpoints. Then we're going to find the integral of f of x dx. Again, we already know what r is. We just need to check those endpoints. So there's a lot going on here, but there's not as much as there could be. All right. So let's just get started. Let's start from the very beginning. I'm going to write it over here. F of x. Can you still see that? Yes. The center is going to be 0. Because remember, the center comes from x minus c. We don't have a minus c here. So we're just going with 0 as our center. So I'm going to start off with the limit as x approaches infinity of x over 3 to the n plus 1 over x over 3 to the n. Okay, and I don't have to do any fancy stuff here. I have something to the n plus 1th over that same thing to the nth. That's just going to be the limit as x approaches infinity of absolute value of x over 3, which is just going to be, well, there's no, I'm sorry, these limits are as n goes to infinity. That would have really changed things. Yes, as n goes to infinity, does this change at all? No, there's no n left, so this is just x over 3. All right, so there's my limit. We have convergence when the limit is less than 1. So we want x over 3 to be less than 1, which means we want the absolute value of x to be less than 3. Guess what our interval of convergence is? 3. All right, this means we're going to converge on -3 to 3, because that's where the absolute value of x is less than 3. All right, so my radius of convergence is going to be 3, because the distance from the center to 3 is 3. The distance from the center to -3 is 3. And my interval of convergence is going to be, well, it's going to go from -3 to 3, but I don't know about the endpoints yet. I have to check those. And I know I'm walking off screen. I hope that doesn't bother you, but you really should be used to it by this point. All right. So now I'm going to check endpoints for this series when x equals 3. All right, what do we get? Well, we get the sum from n equals 0 to infinity of 3 over 3 to the n. Oh, this looks very familiar. This is going to be the sum from n equals 0 to infinity of 1 to the n, which is the sum from n equals 0 to infinity of 1. All right. So let's be a little more specific. This is going to diverges, because the limit as n heads to infinity of a sub n, which is the limit of n heads to infinity of 1, is not equal to 0. Okay, diverges nth term. The limit of a constant, which is 1, is just 1. So that means we diverge at 3. So we'll be open at 3. Now, you may remember the example we did the other day and be way ahead of me here, because if x equals -3, we're going to get -3 over 3 to the n. So this is going to be n equals 0 to infinity -1 to the n. And again, if we look at the limit as n heads to infinity of a sub n, which is the limit as n heads to infinity of negative 1 to the n, this does not equal 0. In fact, it doesn't equal anything. That limit does not exist because this doesn't go to one value. It goes back and forth. It oscillates between negative 1 and 1. It just flips back and forth. Therefore, it never goes to one value, which means the limit does not exist. And if the limit doesn't exist, it can't equal 0. And so this diverges by the nth term test. Boom. So that's f of x. We have shown that the center is 0, the radius of convergence is 3, and the interval of convergence is open from negative 3 to 3. Now here's what I meant a while ago when I was talking about derivatives. As we take derivatives of this, we are never going to gain an endpoint in our interval of convergence. So actually, I know right now that my derivative is going to have the interval of convergence negative 3 to 3. We're going to check it anyway just to get some practice at it. But I know this already. Now what I don't know is what that derivative is going to be. So let's find it. All right. We have this nice formula that told us to find the derivative, it's going to be the sum from 1 to infinity of n times, I got to be real careful here. Okay, sorry about that. I left a step out in my notes, so I was a little confused. It's right. Basically, we're taking the derivative of x over 3 to the n. And we know, power rule, it's n times x over 3 to the n minus 1. But by the chain rule, I have to take the derivative of x over 3 times 1/3. All right? So it's just the derivative of that. Now, what I did in my notes is I kind of cleaned this up. I have n, and then I have 1/3, and this is like 1/3 to the n minus 1 times 1/3, so that's 1/3 to the n times x to the n minus 1. That's just the way I wrote it, and that n was throwing me off. I had to see where that came from. All right, but this is the derivative. Basically, to find the derivative of a power series, we're going to change this, and then, well, we just take the derivative of whatever our original thing was. And again, x over 3 to the n minus 1, you got the n out front. You have to take the derivative of the x over 3, which is where that other 1/3 comes from. And then it just cleans up algebraically a little bit to this. Now, by the theorem we had written to go, I didn't call it a theorem, but it's a fact, the radius of convergence is going to be 3. So if I were to come over here and say, well, f prime of x, the center is still going to be 0. The radius of convergence is still going to be 3. And the interval of convergence, I have said, is going to be negative 3 to 3. Because this derivative process will sometimes make us lose endpoints in our interval of convergence, but it never makes us gain it. But it won't hurt us to check it. All right, so let's say what happens if x equals 3. We get the sum from 1 to infinity of, all right, we get n times 1/3 n. Do I really want to do it this way? I'm going to use the original here. I'm going to say n times 3 over 3 to the n minus 1 times 1/3. All right. What is that? Well, that's the sum from n equals 1 to infinity of, this is just 1. N times 1 to the n minus 1 times 1/3 Well, that's just the sum from n equals 1 to infinity of 1/3 n. All right, and that is, what is this? This is going to diverge. How do I know that's going to diverge? Because the limit as n heads to infinity of 1/3 n equals infinity, which is not equal to 0. All right. Nth term test tells us that this diverges. Now, just quickly, what happens? -3. This is -3 over n. This becomes -1 to the n minus 1 over. That means, okay, what is this going to be? This is going to be 1/3 n times -1 to the n minus 1. And this is also going to diverge because the limit as n heads to infinity of 1/3 n times -1 to the n minus 1 is not equal to 0. The limit of all that is not equal to 0 because that limit doesn't exist. Again, because we've got this oscillating part. It's getting positive and negative, and it's actually going farther and farther out. So we're getting farther away from 0, but one's negative, the next term is positive. So they're just constantly getting farther away from each other, which means the limit's definitely not going to exist. So yeah, it worked out exactly like I said. Both of those endpoints are not in the interval of convergence. We didn't have to do that work. In fact, I kind of went through it a little quickly. But, you know, there it is. All right, so now let's do the last part. And this will actually finish this up in power series. I want to look at the integral. So I want to find the integral f of x dx. Okay, remember that's the sum from n equals 0 to infinity of, actually it's c plus the integral, the sum, n equals 0 to infinity, integral x over 3 to the n dx. All right, we have to integrate this now. All right, this is going to be c plus the sum from n equals 0 to infinity. This 1 over 3 to the n has no x in it, so I can bring it outside of the integral. X to the n dx. So what do we get? C plus the sum from n equals 0 to infinity of 1/3 to the n, x to the n plus 1 over n plus 1. There we go. There is our series. Not the prettiest series, but it's what it is. Now, so coming back over here, for integral f of x dx, the center is still 0. The radius of convergence is still 0. The integral of convergence is going to go from -3 to 3, but I don't know about the endpoints, and I have to check those. All right? So let's just check right under here. And actually, to check convergence, we don't really need to know about the c. If something is going to converge, then it's going to still converge if we add some number to it. This is a finite thing. It's not going to change anything. Therefore, we really just have to check this term for convergence, the sum. So I'm going to look what happens if x equals 3. Then we're going to get the sum from n equals 0 to infinity of 1/3 to the n, 3 to the n plus 1 over n plus 1. All right. The sum from 0 to infinity, 1/3 to the n times 3 to the n over n plus 1. And hopefully you see where this algebra is going. The 3 to the n and the 1/3 to the n are going to go away, and we get 3 over n plus 1. That's all that's left. Okay. Is this a convergent series? Well, yeah. It's a convergent sequence. And that's what I really started to say. I really started to say, well, 3 over n plus 1, that goes to infinity. But actually, let me rewrite this just a little bit and see if you can tell me if it converges. I'm going to bring the constant out front, 3, times the sum. And now I'm going to change the index. Instead of starting at 0, I'm going to start at 1. Okay, and if you increase the index, then you have to decrease all the instances of your variable. So this is 1 over n. All right, 3 times the sum from n equals 1 to infinity, 1 over n. That's the harmonic series. It diverges. Okay. Now, you may not have recognized that initially, but you have to kind of get used to these things. And you have to think in terms of, well, 3 over n plus 1, that's really close to 3 over n. So even if we could not have rewritten it as the harmonic series, we could have probably done some sort of comparison test and shown that, yes, this does diverge. So that means we diverge at 3. But remember what happens, and I told you this. When you have something converge, when one of these things ends up being the harmonic series, the other one almost always ends up being the alternating harmonic series. So let's see what happens if we have negative 3 in here. And this is going to be some uglier algebra. So if x is negative 3 to the n, we're going to have 1/3 to the n multiplied by negative 3 to the n plus 1 over n plus 1. And I'm going to do a couple of things here. Now, I'm going to say this is negative 3, all right, times negative 1 to the n times 3 to the n. And if you multiply these two things together, negative 1 to the n times 3 to the n, you get negative 3 to the n. If you multiply that by negative 3, you get negative 3 to the n plus 1. I'm just short on board space, so I'm trying to do a couple of things at once. Oh, and there should be a 1/3 to the n at the beginning of all that. 1/3 to the n times negative 3, 3 to the n, negative 1 to the n, over n plus 1. Why did I do that? Because these things are now gone. All right, what are we left with? Well, we're left with negative 1 to the n times negative 3 over n plus 1. I'm going to do the same kind of rearranging I did a minute ago. I'm going to take the constant out front. I'm going to change my index. This becomes negative 1 to the n minus 1, 1 over n. All right, now this is a little different writing, a little way different than the harmonic series we're used to, because we're used to negative 1 to the n, but negative 1 to the n minus 1 is just another form of the harmonic series. It will still converge, and therefore if this converges, negative 3 times that converges, this converges. So this is the alternating harmonic series that converges, which means we converge at negative 3. All right. This stuff gets really tedious and technical, like right there, where we rewrote those things to kind of see that they converge. Remember that a lot of times you're going to get alternating harmonic series and harmonic series. A lot of other times you're going to get that thing where you just add up one to infinity and the other one ends up not, the limit doesn't exist. So those two things happen. Pretty much that's what you're going to see. And this is how you do derivatives and integrals. It's not hard. It's just a bunch of details and it's very tedious. So that finishes up 9.8. Next time we're going to start on Taylor series and stuff, and that's going to be what I really love to do. I love all of this, but that's just really cool to me. So until next time.